I'm finished with what I wanted to talk about today, but before I'm attacked by Victor, I would like, of course, I would, since he interrupted me, I'd like to say two things.
So, you must read a little bit nature for unveiling her.
Yes, exactly. So first, a comment on Francesco's lecture this morning, which I think is, maybe we'll shed light or maybe we'll confuse everybody. So just a little remark, because there was a discussion about second gradient and things like that. So here is a problem which is a classical problem of homogenization. And so here it is. So you have a square. So that's what is called in the language of periodic homogenization Y, usually the period cell. And you have you have a domain which is made of two parts, a part Y1 and a part Y2. And so that's the subdomains. And I'm going to call characteristic function chi1 that of Y1. So that means it's a function which has a value 1 on Y1, 0 on Y2, and conversely, chi2, so chi1 plus chi2 is 1. Okay? And I'm solving the following problem. Minus divergence of chi1 of x over epsilon plus epsilon square chi2 of x over epsilon grad u epsilon equal f with boundary condition 0 on the boundary. So here I'm going to be censored immediately because I don't have the variational attitude, but you can write it in a variational form. That's trivial here. And it's the same thing. So the question is, what is the homogenized behavior? I don't want to talk about homogenization, but what do you expect is going to happen in the limit as so epsilon, so you have to think of your domain like this with where you, so what is it you did? You put a material of conductivity 1 in Y1, a material of conductivity epsilon square in Y2, and you put it on something of size epsilon. And the question is, what is the limit? And here is what is the limit. It's called the double porosity problem. It's a well-known problem. And it's been studied. So here's a problem that if you're Russian, you believe that it's been done in Russia first. If you're a Westerner, at that time it made sense, you believe that it's been done in Germany first. But, okay, so I'm not going to get into this, it doesn't matter. So U epsilon goes in a certain way that I don't want to explain to a U of x, so that doesn't mean much as I write it like this. But here is anyway what the overall behavior looks like. It looks like this. It looks like I'll add something actually. Yeah, I'm sorry. Go ahead. In this asymptotic expansion, should we put epsilon near? No. It's at order 0. If you're doing an asymptotic expansion, it's the first order in the asymptotic expansion.
Okay, so you mean that the first member of the asymptotic expansion depends on fast variable?
Correct. And then you get this as a solution, plus integral over y2 of v of xy dy equals f, where v satisfy minus Laplacian v plus alpha, let me see, plus alpha v. So it's a function of x and y. And I'm sorry, but I'll have to do that. Minus Laplacian in y of v plus alpha v of xy equals f of x minus alpha u of x with v equals 0 on, so that's in y2 plus v equals 0 on dy2. So you see that you've started with a very simple porous problem. Of course, there's no fluid here. It's much simpler than what Francesco was talking about this morning. But you've started with a very simple problem But because your porosity, because your conductivity goes to zero as the size of your periodicity cell goes to zero, you get a this is non-local. There's no way you can. It's worse than second order gradient. It's much worse. It's
1 second. This boundary omega.
Yeah.
The second boundary is only the external one.
Yes, only the external one.
So you must tell us what happens in the
No, I don't.
boundaries.
No, I'm solving this problem.
Yeah, but I mean.
Yeah, but here it's just normal. It's yeah.
Sum of stress equals zero.
And U continuous.
And you.
Yes, exactly. So here you get a very non-local thing. So in a way, what Francesco is talking about is even very special because he's only considering second order gradients. So in a way, it would be, I mean, here of course it's the second order gradients are of a higher order. Here it affects low order. But you could come up, and actually your friend Sepesher has come up with models where you have fourth order gradient, any order gradient you want. Okay, so that was a comment, not a criticism, of course.
No, but tell me details about this because.
Yeah, I will.
They attack me because it's too much. This answer.
No. It's maybe not enough. That's what I'm saying. So now here, and I'm sorry, maybe I shouldn't do that, but I'll do it anyway. So here, very quickly about Professor.
So we can say in a philosophical way that Cauchy fields are not closed under homogenization.
Correct. Absolutely. So now I would like to address Professor Carpentera's lectures.
Victor, luckily you are leaving too.
No, it's not a criticism. It's just discussion. Maybe
Let us joke.
maybe it's a different view.
I hope it is just a discussion and not a criticism. Because
No, but it's a question of dissipation.
I want to remind you that I didn't interrupt you. So
This is not retaliation for anything. Just maybe to show you that when you talked about, I mean, I didn't follow the details because then I got involved in the computation to try and make sense of sense. But maybe a different light, something which shows you that it's not surprising what he's talking about. And I'm going to write a conservative system and show you that there's dissipation in it. Okay? Whatever. So of course I come from a different world, so I write different things, but it's pretty much the same thing. So I take 0, 1, okay, and I take the function which is 1 here on 0, 1 half, and which is 2 here on 1 half 1. I call this function A of y, with y between 0 and 1. It's a nice function. Okay? And then I solve the following problem. D2u, because his problem was hyperbolic, so I solve something which looks a little bit like a hyperbolic problem. It's a poor man's version of a hyperbolic problem. Now let me be clear. So I solve this in R, let's say, and in R at all times, and u epsilon at 0 and x, because that's a function of t and x, right? T and x. T and x. There are no derivatives in x. Okay, so that's not quite a hyperbolic problem. Equals 1. And du dt 0 and x equals 0. Okay? Nice problem. No problem. You can solve this. It's a differential equation. X is a parameter. And then you say, well, what happens when epsilon goes to 0? So so first of all, you will agree with me that it's conservative. Okay, because so for those who don't see it immediately, you multiply this by du epsilon dt, you integrate over r, and you get that the energy, which is E epsilon of t, which is 1/2 of the kinetic energy integral over r of du epsilon dt squared plus whatever energy here I don't know what to call it, A of x over epsilon, u epsilon squared, dx. This guy is conserved. It's equal to its value at 0. For me, that's what a conservative thing. There's no energy loss in your problem. It's perfectly conservative. I go to the limit. So how do I go to the limit? You can do...
Sorry, you get these equations via a Lagrangian.
No, you can get it via Lagrangian. Yeah, of course. You can get it as a stationary point of du dt squared minus a epsilon u epsilon squared. No problem, via least action. Okay, so you get, it's Lagrangian, it has a Lagrangian, it is conservative. I go to the limit as epsilon goes to 0. So what do? Here I'm not going to be stupid and try to do a theory. I'm going to compute the solution u epsilon at xt. And I know what the solution looks like, unless I made a mistake. It's cosine of a over x over epsilon t. Okay? Unique solution. Cosine of a of x over epsilon t. No problem. So it's an ordinary differential equation. I wrote it like this because it depends on x, but the only variable is t. Cosine because I have 1 and 0. Okay, now the only thing you have to know, which maybe some of you don't know, is that any periodic modulation, when you have a function which is periodic, a of y, you replace y by x over epsilon, you go to the limit, as epsilon goes to 0, it converges weakly, that is against test function, to its average. So this guy converges at all times to u of t, but because it's not going to depend on x, which is the average over the period cell, the integral from 0 to 1, of cosine of ay t dy. Now this, because of that's why I had started with sine, but then I didn't know how to compute things because I had cosine of sine. With characteristic functions like this, it's wonderful because you have an explicit value of this. It's cosine t plus cosine 2t over 2. So the weak limit, the limit in any reasonable sense here, of this equation is cosine t plus cosine 2t over 2. So then you can compute, it's just a function of t, it doesn't depend on x. You can compute its first derivative, its second derivative. So I'm not going to do it, it's not very hard. Huh? So you compute its first and second derivative, and then you say, well, okay, so u is kind of the average. I mean, in any reasonable sense, u is the average of the oscillation of u epsilon in space. So it's very much like if in his problem he had multiplied the number of elements to infinity. Okay? And u would be its x is x actually, so the center of mass or of gravity. So u. So now you ask yourself, so you can compute u prime, u du dt, d2u dt squared. And you ask yourself, is this conservative in u? And the answer is no. There is no, at least, I'm going to qualify my answer. There is no alpha such that so u of 0, by the way, u of 0 is 1. And du dt of 0 is 0. Okay? So the boundary, the initial conditions are kept. You cannot find an alpha such that d2u over dt squared plus alpha u equals 0, with u of 0 equals 1, and du dt of 0 equals 0. There is no such alpha. You can do it. You can do the computation. If you will have a term here. You will have a term here which will dissipate. There is no way to write this, the solution for u of t in a conservative form. So, what does that mean? That means that the idea of conservative is an idea which, I mean, that's my interpretation, and of course you're welcome to jump or react, but that means that the idea of conservative is an idea which, of course, does not pass to any kind of limit, like multiplying the number of elements in his picture, where you'd have more and more of those things, or going to any kind of averaging process. So when he's looking for the equation for x of t, which is the same as averaging, more or less, you are indeed in a situation which is canonically of this type, and so you don't expect the limit to satisfy any kind of conservation to be a solution to any kind of conservative, equation which admits conservation. You introduce dissipation by the averaging process somehow.
Just the conclusion, because it's important.
Yeah.
20 minutes.
Well, no. The conclusion is that maybe you've done something. I mean, I've done something pretty stupid here. I know how to compute the solution. I know how to compute its average. Why am I looking for an equation for the average?
I'm not looking for an equation.
No. You are, because you're trying to get an equation for xt.
X6 is not the average of anything.
Yes, it's the average. It's a center of mass, right?
So?
It had to do. Am I wrong?
No, you're right. No, I was not looking for...
was one of the Lagrangian coordinates. Yeah, there is no average on space and time.
No, just on space. I thought that's what you were doing in a discrete manner. Maybe I misunderstood. Then I'm sorry.
Now there is a relationship somehow, because he had the idea to couple is
But
one
well, maybe he should tell us. You don't think that's? Yeah.
Really speaking, I did not understand what is the point of your. It is not a question, or it is a new presentation. So I didn't really understand what is the point related to what I presented before. In any case, I can do an effort in order to interpret what you are.
It's an analogy. It's not. I'm not.
So I was not looking at average of x. I'm just saying that it is possible. This is not very strange. This comes from very well-known papers in physics that are published by Feynman in the 50s, in the 60s. It is possible to represent the motion of a single particle just taking into account the effect of the environment and just expressing this by a convolution integral. That's it. So I do not understand what is the point here. So I see that there are more or less 6 square meters of formulas, but I cannot understand very clearly what is the link with the things I was presenting.
So maybe I missed you. So maybe the quote. So I apologize. I missed you because I thought that somehow you were trying to describe how your system evolved through some kind of averaging process.
Well, no. It is not the point of the presentation of the model. I introduced the average, but this is something that can be avoided. It's just an interpretation of the mathematical model that you can use in order to obtain the optimal distribution of natural frequencies inside the hidden part of the system. So I just make a comparison between the average, in the sense of the ensemble average of the population system, and the individual response of the system. So it is just a matter of fact that it can be verified very easily without using, say, complicated formulation, that if you just use an asymptotic expansion of a function that contains an harmonic function of time, it goes to 0. It's very easy. It's really very easy to show that it goes to 0. But this is not the property of a simple sample of a system. It has a finite number of degrees of freedom. And this is also something that can be verified everywhere. So if you compare the ensemble average, and you compare the ensemble average with the single case, then you have that they don't share the asymptotic property. That's it is a very easy to prove. Now, what I am asking is, what is the distribution of frequency that makes the average the closest possible to the single center? This problem is not the fruit of my fantasy, but it has its roots in a very beautiful theorem that was proposed in 1941 by Fisher, in 1942 by Koopman, in 1943 by Koopman and another guy that was Pittman, and again in 1945 was well-known as Cramer-Rao inequality. So it is something that is well established as a result of linear algebra together with. So it's something that really.
I didn't mean to be critical, so maybe you misunderstood my. I didn't mean to be critical. I probably misunderstood what you were saying. I was just offering what I thought was maybe an idea for people who are more used maybe to different techniques. This is very simple PDE or ODE type thing. And some of you, I'm sure, are more comfortable with this than what you were talking about. But maybe I missed the point. And I'm glad we tried it.
No,
but I'm just saying that this kind of the fact that thing that you're conservative are not conservative is the case.
Can I understand what is your point about? So the first equation you write down, the first one, you have second derivatives with respect to time. Then you have this is in my notation. You have a function that depends on x. It is just space.
Which is space.
Then the second term is just what is u epsilon. It is an obscure notation for me. What would that mean?
Well, imagine, for example, that you were doing something which with springs everywhere. So
and is epsilon is to indicate a spring?
No, epsilon. No. Epsilon is to be thought of as it's like multiplying the number of.
Is a scale factor.
Yes. You're creating more and more. So
it is an epsilon that you introduce like a perturbation approach.
You're trying to solve. You're trying to solve your problem, putting more and more things like this. So you're in space. Your thing looks like this.
So you are considering an equation like, for example, in which you have periodic coefficients?
Correct.
Okay, this is the well-known theory in which you have periodic coefficients in terms of space.
This is not well known. This is not well known.
It's not.
This is easy, but not well known. This is not classical homogenization.
Well, I don't know, but I don't know what it represents actually. So if you have just the
I was just trying to write the most simple conservative system that I could think of. For me, the most simple conservative system.
Yeah, but I don't know. I don't understand. So, but what is the main concern? So that okay, it is possible to write.
Okay, the main idea what you wanted to say is when you have a system, you average the system, even if the system was conservative, it will be not conservative after averaging is right. But maybe it's not directly right with your.
That's all.
I agree with you. So both of you are right.
But I'm not very well understood the details, but maybe
No, the idea is very simple and he's right.
localized cells in which you have kinetic
No,
energy which is lost.
I agree with you. So if you are saying that averages do not preserve conservation of energy, I agree with you.
I thought that was part of your message, but maybe that's what
But
I.
I agree with you.
That's all.
But this is exactly the result that I want to use. So if you introduce averaging, you have not a physical system. This is the main point. So it is very well known that when in physics you introduce averaging, the average system is not physical anymore.
Okay.
But nevertheless, the property that this non-physical system exhibits is very useful to me. And I use a physical system that mimic the closest possible the non-physical.
I just stopped at the first part of the statement, and I tried to interpret it in my application. Sorry, I will take a big conversation where.
No, it's okay. So it was very interesting.
But
It was fine. Yeah.
Yeah.
Victor wants to say something.
If I may.
Oh, you can say whatever you want.
We keep on the table. You know, I'm actually very slow thinker, so I'm skilled on this example, and I didn't get the point here. Look, if the problem is exactly as you wrote it here, then this is the cell problem for you, and it can be solved immediately and exactly. And the solution of this problem is, and the solution of this problem is the following. Say, we have here, this is Laplace operator over Y. V, as I can guess, is a periodic function over Y, which is...
No, it's only on Y2 you're solving.
So this is Laplace operator over Y.
But you're only solving it in Y2.
Why? Just a second. You have periodic cell, right? You have a periodic. What is this problem? I just
Sure.
What is it?
I'm solving this.
Okay.
In this domain, Y2 is zero boundary condition.
What is the region of
Y2.
Y2 is what? Is this one? What about?
I'm solving it on Y2.
This is the prototype cell before swinging in
that's
epsilon.
All right. Then okay. Then I skip what I actually understood. As far as I know, homogenization, the problem which should appear is the problem for V on the cell, and of course you can have V equal to 0 on
No, because you have compactness on Y1.
All right.
So you don't
Okay,
need isolation.
okay. I withdraw my.
Okay, good.
And for
Once
but
it's
now I.
out.
But one thing I would like to say, which seems to be quite important, and this is to explain why I understood so poorly at the beginning of Francesca's lecture. And I think this point is, especially since we have here very young, very nice, very bright faces, and it's so nice to see all of you from this point. And what happens, people of this age like to trust all that they read, all what is published. And you will see in the current literature a lot of so-called direct vector notations. And say you may see, as we have seen today in a very nice Francesca lecture.
I stop you. I am against the absolute notation American way.
No,
I don't
present American or Russian or any other.
No, there is only with all indices.
Sorry?
There is only one absolute notation. Levin, Chivas, with many indices.
Okay, this is the point to which I am coming. Yeah, exactly.
There is only one field.
Yes, all right.
One cross.
Okay, now let me explain why. Yeah, I completely agree with that. Levi-Civita notations are the most clear ones, no questions, but these are not the notations which are currently mostly used in the literature. And I would like to say why these direct vector notations are not so good.
I will send you a paper in which I attack people who are not using Levi
good.
Francesca.
Now let us come to our you might see For example, people denote strain tensor by letter epsilon, and they assume that epsilon is a tensor, and then they can write that say energy or internal energy is a function of epsilon, function of a tensor. What is bad about it? Let us start with a vector. So what is vector? If we have a say, let us take coordinate system x1, x2, x3, and then this coordinate system has basic vectors, say e hat 1, e hat 2, e hat 3. And you can write that vector is the sum of the components and basic vectors. And what we see from here, that vector is determined not only by the components of the vector. Vector depends also on the basis. And so if we take the same components, but we take another set, another basic vector, another basis vector, we get another vector. So when we say vector, we include in this notion two objects, two different objects. The set of components of the vector and also the basic vectors. The same pertains to tensors. Say if you have tensor, if you have a tensor, then tensor has, or if you can write tensor in this way. And so tensor also, if you use direct notations, then direct notations include not only the components of the tensor, but also basic vectors. Now, if you write, for example, such a relation, what does this mean? That means that you include in energy arguments on which energy does not depend. Energy does not depend on the choice of basic vectors. Energy depends only on the component of say strain tensor. I cannot finish just a second. Now, but this is not all. The problem is that in continuum mechanics we have several important set of basic vectors. If we have a continuum, say we take here some piece of continuum, and and in order to describe the motion of continuum, we have also to introduce Lagrangian coordinate frame, some set of coordinates here. Lagrangian coordinates, let us denote them by x capital. And then this continuum is moving, so this piece of continuum is changing, and this Lagrangian coordinate frame changes. We get here additional basic vectors. We get, say, at the initial instant, we have basic vectors, say, let us denote them by E hat A, maybe I put, instead of hat, I put here 0 to say that this is initial basic vector, and when it deforms, we get here another set of basic vectors, say E hat A. And therefore, we may introduce, actually, with the same components, say we take strain tensor, we take, say, the same components of the strain tensor, but we may introduce different tensors, because tensors involve also basic vectors. So we can introduce, say, tensor epsilon 1, which is, I put here, E not A, E not B. I can introduce tensor epsilon 2, which is, I take the same component, but now I take different basic vectors. Say this would be E hat A, E hat B. I can take vectors, strain tensor, say epsilon 3, which is epsilon A, B, E not A, E hat B, and so on. There are some variations. So there could be many possibilities. And when we write such a thing, it is now when I see such an expression, I am wondering which one is being used, this one, or this one. And this is not a so to say, a shallow question, because of course, you can use such a form, but you cannot. What is hidden here and is not said explicitly, you can use this notation, but what is not said explicitly here, that there must be additional tensors inside this energy in order to make a scalar. And which additional, and actually these additional tensors determine which internal energy you have in mind. Again, example, say, let us denote by G naught the following tensor. I take metric tensor in the initial state in Lagrangian coordinates and put here, say, and put here E naught A, E naught B. If I write that U internal energy is a function of epsilon, say epsilon 1, and G naught, that this determines complete. So we included here also additional arguments, the basic vectors. But the fact that this is scalar tells us how to eliminate all these additional arguments. And say if we require, for example, that this function must be linear with respect to strains, then we end up with the only combination that there is some coefficient lambda times, say, G naught AB, epsilon AB. And this is that's all we can have. But if we include here tensor epsilon 2, then we will get different function. Or if we include epsilon 1, but instead of G naught, we will include tensor G hat, say, I take metric tensor in actual space and put here, say, E not A, E not B. I will get, say, if I put here G hat, I will get another internal energy. So when we use direct tensor notations and say if we just write U is a function of epsilon, it is not clear what
You are right. Okay. I needed to say something which I didn't explicitly say. So in a sense, I did not explain the basics of continuum mechanism.
Yeah.
So I have as
Francesco,
point.
this is not a criticism.
No. Look, this is exactly what, I am from a school in container mechanics, deep south Italy,
Oh, okay.
Naples, which is now disappeared because they all retired, my professors. And I was chased by them. We started this way. You have a vector space without basis. And you have a affine space, E, which is a set of points. Then you have addition between points and vectors, and this belongs to E. And you construct the structure of point affine, the structure of Euclidean space with this logic, and you never talk about basis. And my epsilon, you have now two of these animals, V1 and epsilon 1, V2 and E2. Your reference configuration is a subset of this. Your actual reference is a subset of that. Then you have a material segment, capital V, and you have the gradient, and you never talk about components, because this is a vector space. You have a norm here, so you can linearize everything. And small v is f of capital V. And epsilon is f transpose, f minus identity over 2, where f transpose is the lab such that this times this is equal to this times that.
All right.
So we never talk about basis.
In South Italy, so they have some special set of notations, set of rules, and when they write expression like this, so they mean something special. But in North America, this could mean quite different, something different.
Because
all right.
Trustedt did not understand very well Tolotti's book when he translated in English. This is the problem.
All right. But now, the point which I am trying to make is that if you use, instead of direct tensor notations, component notations, you don't have any uncertainties or any ambiguity.
No, because if you change your basis, the components change.
No, in a sense, but yes and no, because if you write, say, instead of, let us say we have Lagrangian coordinates x capital, and we have the x small are Eulerian coordinates, and you write, and your displacement gradient you write as usual partial derivatives. And when you put, and when you say that internal energy is a function of this component, and you can write, if you need it, you can write this function explicitly. You don't have any ambiguity. So
Now
that's
you have to tell at the beginning which is your basis.
this function does not.
Now, if it depends on the invariant.
Well,
If you use Ehringen notation and you introduce the invariance
all
of
right,
this,
all right.
then
I made my point. So my point is
this is changing with change of value.
right, but energy is a scalar. So in any coordinate frame, it has the same shape, the same form. So since energy is a scalar, it doesn't matter which coordinate frame you use. Say Lagrangian coordinate frame, Eulerian coordinate frame, etc. All right. So we may have agreement, disagreement, but this is I think I made my point clear. the coordinate presentation does not leave you any ambiguity. Now this is the second problem. And this actually this is the issue of boundary conditions when we come to fluids. It is not elementary. Well, it is actually a very complicated issue. Say, as we discussed, we have a say flow in the pipe. Let this pipe be two-dimensional. You consider that porous. But now let us simplify the situation and assume that there is no solid resistance, just pure fluid. Just pure fluid. And let it, again, I do it as simple as possible. Pure fluid, incompressible, steady flow. Equations for this case are very simple and they are well known. You have to, so equations are, for steady flow, you take velocity of the flow multiplied by gradient of vorticity. This is equal to 0. You take, say, what else do we know? We know that the velocity, link between velocity and string functions, and I use Levi-Civita symbols in two dimensions, E alpha beta, say C dx beta. And the third equation of the system is equation which links string function and vorticity. So the last equation can be viewed as the definition of vorticity. And now the question is, what should be the boundary conditions for this system if we have just a flow in the pipe? This problem was attacked for the first time in 60s, and solution was given by the famous mathematician Victor Yugovich, and he suggested as such boundary conditions the following ones. Of course, on the wall of the pipe, we should have the condition which means that fluid does not penetrate through the wall. So normal component of velocity is 0 on the walls. And now, what should we put at the on the inlet and the outlet?
Vorticity? Vertex?
How? On both sides?
No, just the.
Yeah, right. So what we also have to prescribe here is, as was suggested by Yugovich, is the following. We have to put on this side, we have to prescribe normal velocity, say, let it be, say, phi, some given function, say phi1. On the other side, we have to prescribe normal component of velocity, say, let it be phi2. But this is not enough, and as Sergei mentioned, we also have to prescribe the vorticity at the entrance of the at the inlet. Say fluid moves in this direction, so at the inlet we also have to prescribe vorticity. Vorticity, say, is some given function, omega. And he proved that with this boundary condition, this problem is has a unique solution, etc. Now, these conditions are not, first of all, these conditions are not for Ation. You cannot get these conditions from a variational principle. Number one, though the ideal incompressible fluid is a very nice Hamiltonian system. And numerical simulations, which has been done recently, discovered the following strange phenomenon. That if you say you have some artist, say, let's say, point vortex enter the region. So point vortex enter the region, it travels somewhere, somehow, but then it doesn't leave, it may not leave the system. So when it depends on the value of the normal velocity prescribed at this site. If it approaches this point, instead of leaving the pipe, it can go back somehow.
And the compatibility conditions.
Yeah, there are compatibility conditions of what the discharge, the discharge of the flow on both sides is the same. So what to do? And the answer is open. There is no clear answer how to formulate boundary conditions in this very, very simple case. Even there is no porous media, just in this simple case. In my book, the first edition of the book which I was referring to, which was published half a year ago, and so the previous edition was about 30 years ago. In this first edition, and I kept it in the second edition, some boundary conditions were derived from the variational principle for the fluid, but it is still unknown whether it makes physical sense. So whether these boundary conditions avoid such an effect. And by the way, these boundary conditions were based on consideration as field variables in variational principle, Lagrangian coordinates. So this is very reminiscent of what you described when you talked about porous media. Again, I would like to call your attention to that even in this simple issue without any porosity, we have quite fundamental open questions.
I am also slow as you are. So if I double the scale in my vector space at the beginning, this derivative becomes 2 times and the energy is the same. So you are in track.
Okay, we agreed that 80%, and actually I cite your words, that 80% is of papers written in quite understandable way. I believe that each author, if he put in the corner and asked with some persistence, will eventually be able to spell out all hidden things in the paper or say make everything clear. Usually in usual publications of text it is not done. The reader must do some additional thinking and make sense of what.
I think that the clearer treatment of this in this aspect is in Eddingen, where you have the invariance of epsilon in you written in God. Because as you write there, it's not well posted.
Well, I will not.
So it is late. Let's go to Eddingen.